expanded to this particle in the box. Yeah? So we start with this quantum effect, and then in the quantum effect, this is the textbook diagram. So we first engage this X-ray light source, okay, to observe the scattering. Now, in our earlier context in the optics, we also learned about scattering, isn't it? And then at that time, our scattering, okay, was examined with visible light sources, so like the sunlight. And then based on the polarization, we also know that after scattering, the polarization is somehow affected by the scattering effect. But now, instead of the visible wavelength, we want to use this X-ray. Why we have to use X-ray instead of visible light source? Any idea? Why do we want to use X-ray?
Use the formula.
Sorry? Yeah, why do we want to use X-ray? Have you used visible light? So any idea why do we want to use the X-ray? Okay. Any idea? We want to use the X-ray because its wavelength is very, very short, isn't it? So wavelength of the X-ray is a few nanometers, so very, very short. It can actually see the atomic level, alright? So you can see the atomic level. Therefore, we now talk about the quantum physics. Yeah? So quantum physics is a physics handling or understanding very small size, yeah? So atomic level size. So that's why we engage X-ray, alright? Then this X-ray now incident on this metallic target, and then we now this quantum and his colleague observe that when the X-ray incident on this target, and depending on the scattering angle, okay, depending on the scattering angle, the scattered wavelength is different. So scattering wavelength is dependent on the scattered wavelength is dependent on the scattering angle. So this is formulated down here. Alright, so our angle, okay, so the wavelength of the incident photon and the wavelength of this scattered photon is related to this constant and then scattering angle. Then, how are we going to measure this scattering angle? Our scattering angle is going to be defined, as you can see in the diagram. We will first extend this incident photon line. Okay, we will extend the incident photon line. And then the angle is going to measure from the extended line to your scattered line. Okay, so this is your angle. Alright, so now we have now this mathematical expression for this quantum effect. And then obviously this electron is going to be scattered too. Yeah? Electron in the target going to be scattered too. And then we will use these electrons scattered angle too if we want to calculate the electron behavior after the scattering. Alright? And then why this is then so important in the quantum physics? So if you want to compare this with to the classical physics, in the classical physics, when any instant wave, okay, onto this metal is going to push the electrons, isn't it? It's going to push the electrons, and then the electrons, because the electrons are in the different initial states, well, their initial conditions are different, therefore, when they are pushed away by this X-ray, they will travel at different speed. So electrons will travel at different speed, which means we should be able to see various Doppler effect, so various Doppler frequencies. So in classical physics, we would expect the spectrum like much broader like this. Okay? But then from the quantum effect, it was found that it's not actually true. When the scattered angle is defined, then its corresponding scattering wavelength is fixed. Okay, it's very well defined. So that's why this becomes an important result for supporting this quantum physics. So here, as you can see, we now treat this light 100% as a particle. Okay, this is the scattering, particle scattering, as you learned in your previous semester. Yeah, elastic scattering, inelastic scattering, and then we use 100% the particle model to interpret the light. Then this idea is expanded to the de Broglie wavelength. So in the de Broglie wavelength, now we relate this particle and then wave, okay, in an equation. Alright, so then now we see that if we are given any particle behavior of the light or photon, then we can actually find its corresponding wavelength. Alright, then because of this region, this idea is then expanded to the wave function, isn't it? This idea is now expanded to the wave function. So, particle is given, okay, and then this particle is this particle will have the wave nature, wave property too. Therefore, this particle can be described or explained in terms of wave function, okay, wave function. So then, when wave function is given, and you know this wave function will give us this wave. Yeah? So then, from this wave function, we still want to know the location of this particle. Okay? Then, the location of the particle is now met or calculated using this probability. Okay? Using this probability. So, your probability is normalized in most of the cases. So first of all, your probability is calculated as, so if the wave function is given, then your probability is going to be calculated as this. Okay? And then, if you do this integration from minus infinity to the plus infinity, then this is going to be 1. So, and then we call it normalization, okay? And then, which means there is a particle, okay? Somewhere in this space, okay? Somewhere in the space. And then if you want to narrow down the region, then your probability, let's say, I want to find this probability of the particle, let's say, from minus 3 meters to 10 meters, then your probability is going to be calculated as this. Okay, so you will set your region of interest to find the probability. Alright? Then I will now move on to this Bohr's atomic model. So Bohr set a few assumptions, okay, to come up with this model. The first one is electron moves the circular orbit around the proton. Okay, this is obvious now for us. And then certain orbits are stable. In other words, certain orbits are stable to hold the electron. Okay, so this means actually this implies that the orbits are discrete. We don't have a continuous orbit. Okay, so the orbits are discrete. And then the photon, if there is any energy transition, okay, of the electron, this will generate, or this energy transition is going to appear as the photon energy. Okay, so this relation somehow are very often illustrated in this. So where we draw two horizontal lines, and then the lower horizontal line has the energy level of 1, and then let's say upper horizontal line has the energy level of 2, and then electron in the second level will decay to this lower level, and then this energy difference, okay, this energy difference will now appear as photon. So if we have the activation, this will generate photon, and then if we have the absorption, so if we have the excitation from lower ground to the upper ground, then this accompanied with the photon absorption. Okay, so this energy gap difference, okay, energy gap between the energy levels is now well, appear as the photon. Okay, so we are going to use the photon energy to understand this energy transition, alright? And then another important assumption that Bohr made is this. Electron orbital angular momentum, okay? Electron orbital angular momentum is discrete. So again, we don't have any continuous this orbit, alright? So we have a discrete orbit. Then I believe in your lecture, all these assumptions are used to derive this final equation for this energy. Then this derivation might be a bit lengthy in your lecture, so I just summarize this derivation, the working in this slide. Okay, so first of all, we first start with this idea. So this electron is circulating on the orbit, circular orbit. Therefore, there is a centrifugal force in it. There is centrifugal force. So we have the centrifugal force. And then this centrifugal force is actually the electric force between proton and the electron. Okay, so we have a proton and the electron, and then they will attract each other because they are in the opposite polarity. So our centrifugal force is actually the electric force. Okay, that's the first thing. And then the energy of the system is the kinetic energy plus potential. Kinetic energy plus the potential energy. And then you may want to pay attention to this total energy. So the final equation, okay, the final equation does not tell you the electron energy. This is the energy of your total system. So we consider potential energy as well as the kinetic energy. Okay, so potential energy means we actually take into account the proton in the equation. Okay, so this total energy should involve the kinetic energy of the electron as well as the potential energy acting between the electron and the proton. Okay. So while your kinetic energy is simple, alright, and then while your potential energy between two charges, we already learned this in the electricity and the magnetism. Yeah. So this is the Coulomb constant times the charge 1 times charge 2 divided by the distance. Alright. So we have this negative sign. Why do we have a negative sign here? Why do we have a negative sign here? Because the proton has positive charge and the electron is negative charge here. So because of this opposite polarity, we have a negative sign. And there is no such thing like potential energy is reduced or whatever. Okay, potential energy is there, but we have a negative sign because of the opposite polarity. Now finally, we use this the other assumption that Bohr made. The electron orbital orbit is discrete. Alright, then you are going to combine this first equation and then third equation, okay, to derive this. So the distance or the radius of your orbit is going to be determined as this. And then if you have a good eye, then you can immediately see that these are all constants. Okay, these are all constants. And then we have only difference in the n. So this n is integer number for your the orbit. Yeah, orbit. So n equals 1, we talk about the first orbit, or n equals 2, we talk about the second orbit, so on and so forth. So this makes sense, yeah? So the distance between the proton and the electron will increase with this higher orbit. Okay, this makes sense. And then we are going to substitute this into this second equation. This will give you this energy of the hydrogen. Alright? Then again you can easily find that these are all constant. Okay, so well we will have this energy dependence on the orbit state. Okay, on the orbit state. So well back to this diagram. So this is the innermost orbit, so whose this n is going to be 1, and then I can draw another orbit. Okay, so this is n equals 2. So this electron can jump up to this n equals 2, the second orbit, or the electron in the second orbit can also decay down to the first orbit, and then that energy transition is going to be accompanied with the photon energy. Okay, photon energy. Alright, so electron energy change is going to be related to the photon energy. Okay? So this is also our conclusion was also where we actually have done this experiment in our lab. When we engage this grating and then the mercury lamp and the helium lamp, what did you see? After the grating with the mercury and the helium, what did you see on the spectrum? You actually saw the discrete lines, isn't it? Discrete lines of the spectrum. So those discrete lines actually generally originated from the energy transition. Okay, and then this was also explained in your lecture slide as a Feynman series. Alright? So now I have one question for you, since we now understand about this tubular wavelength. So an electron and then proton, okay, they both have the same tubular wavelength. But then each of the following quantities is going to be the same for those two particles. So speed, kinetic energy, momentum, or frequency. So proton, electron, they now behave as the same wavelength, okay, same wavelength. Then each of those can be also same for those two particles. Yeah, well, you don't need to be silent. Well, what do you think? Are you going to speak or kinetic energy, momentum, frequency? We can be wrong, yeah? So what do you think? Frequency, very good. And are you ready for one more vote? You can check out this paper. So, do you have any other suggestions?
呀，我用这个，可是两个很多都在里面。As in like
两个打不到人。
Momentum, okay.
你要先做前面
very
的，
good.
你要先做
So,
PhD 的。
let's see, okay. So, we learned that this the momentum, okay, our momentum is in the classical physics. This is mv, isn't it? In the classical physics, and then through this tubular wavelength, now this is now related to the wavelength as this. Alright, so obviously from this you can see that if wavelength is the same, then the momentum is going to be the same. Okay, momentum is going to be the same. Now, what about this mass? The proton and the electron, they carry different mass. Okay, so the mass are different. In other words, the speed are going to be different too. Okay, speed for the proton and the electron are going to be different too. Yeah. And then let's engineer. So speed is not the correct answer. Yeah. Then let's move on to this kinetic energy. Our kinetic energy is calculated with
做这个
this.
的，
We
这个快
already
的。
we already found that the mass and then velocity, they are in the different quantities. So in other words, the kinetic energy is not going to be the same for the electron and the proton, so we can remove this. Alright? Then what about the frequency? So your let me see, your energy, okay, your energy, so kinetic energy of these particles is actually now described as this photon wave with the wavelength, so this is going to be h. Okay, so kinetic energy are different, therefore our frequency is going to be different.
没有什么 sub value，
Alright?
多少
Frequency can be different.
什
So
么水？
the correct answer is momentum.
已经多少？多少？不要死。
Now I will move on to this Schrödinger equation, but here I believe we will have time to talk about this Schrödinger equation in the next tutorial. But for now,
他在讲
what we want to know is this. So if we are given the wave function, then from the wave function you can always determine the probability. Okay, the probability by calculating this. Right? Now, so let's have a look at, let's practice this, okay? So we are given this wave function, okay? And then
you use the speed.
where do we have the highest probability to find this wave or to find this output? Okay, so this wave function is given, then where can we find, where do we have the highest probability, okay? To find this output. So at which region is our lucky region? So when we learn that the probability is going to be calculated as this. Alright? And then, well, let's try to calculate this. Alright? So integration of this wave function square, so a exponential I k x. And then this is a complex number, so I'm going to multiply this complex conjugate. Then this becomes a square dx. Isn't it? So this is constant value. Okay, so this is constant value. So we are going to have the same probability along this x-axis. Alright? So we are going to have the same probability. So now we understand how to use this probability to find how to use this wave function to find the probability. Now this wave function is now developed to the particle in the box. So here, well, we assume that an electron or the particle is somehow trapped in this potential well, and then well, the electron cannot just stay anywhere as it reaches. It must follow this discrete energy levels. When the electron or when the particle is in the lowest level, then its wave function is going to be described as this. And then at the second level and the third level, we can see that how this wave function evolves along this kind of energy levels. Yeah? Our interest is to find the probability. So our probability function or density is going to be calculated as this, yeah? And then their corresponding the probability is also illustrated here. So our question is then, what would be this around wavelength? Okay, so these are these wave functions, then what are the around wavelength for this wave function? Then if you examine those figures, then you can easily see that this wavelength is related as this. Okay? So in the lowest level, the wavelength is actually 2 times this box length, okay, length of the box. Then we want to we want to define the wave function, okay, for these behaviors. So, well, because this is a wave function, so you can come up with very combination of the sine and the cosine. Okay, you can do that. But we also want to make this mathematical expression simpler, isn't it? So we just want to start with cosine or sine, and then when you look at this diagram, our sense of choice is going to be sine, because at the initial point, okay, at the initial point, its wave function is 0, isn't it? At the initial point, your wave function is 0. Therefore, it makes sense to choose sine as your wave function. Yeah. So sine is choose our wave function, and then we just substitute this into this equation. Then we now come up with a very nice wave function that describes this particle in a box. All right. Then since the wave function is determined and the wavelength is also determined, now we want to find the actual energy of this particle at different levels. So we use this Debrouille wavelength, alright, and then you can easily derive this equation. Okay, and then again, your energy is linked to the energy state. Okay, energy state. So I think I covered all the topics used for this tutorial question. So I'm going to start this tutorial question. So tutorial question number 1. A photon having wavelength lambda scattered over free electron at A, producing a second photon having wavelength lambda prime. Alright? And then this lambda prime then scatter off another free electron at B, and then producing a third proton having wavelength lambda 2 prime, moving in a direction directly opposite the original photon. Okay, we want to determine this wavelength difference. So this is about the quantum effect. So we are going to use this equation. Yeah? So let me first copy this diagram. So at point A, the electron is at rest initially, and then photon incident on this electron, and it is scattered off to this direction. Okay, so it's lambda. And then at point B, this is scattered off again with lambda 2 prime. And well, we want to find the relation, okay, between this lambda and the lambda 2 prime. So most likely we are going to apply this quantum effect for the scattering A and then scattering B. Alright? So in order to apply this quantum effect equation, we must first identify this scattering angle. So I'm going to define the scattering angle as first I will extend this incident line, incident photon line behind the event of this scattering, and then the angle from this extended line to this scattered photon is going to be angle. Okay, so I'm going to take this angle theta 1. And then this scattered photon now becomes incident photon to this electron at point B. So I'm going to extend this again, and then this is going to be angle theta 2. Right? Then immediately you can see that because those two lines are parallel, these two lines are parallel. So if I extend this, then this is angle theta 1. Alright? So then angle theta 2 is going to be 180 minus angle theta 1. Alright, so now let's set those two equations. So at the scattering A, you can say that lambda minus lambda prime is equal to lambda c 1 minus cosine angle theta. Alright, and then at the scattering 2, we can set as lambda prime, lambda 2 prime, lambda c 1 minus the cosine now 180 minus theta 1. Okay, so this is theta 1. So what is this? Cosine 180 minus theta? Very good. So it's a minus cosine theta 1, yeah? Very good. So this is going to be angle c, lambda c, 1 minus to become plus, yeah? Right? So because we want to find the relation between lambda and the lambda prime, so we want to remove those lambda prime, yeah? So how are we going to do this? We will just add those two equations. So now we will have lambda minus lambda 2 prime equals lambda c 1 minus cosine theta 1 plus lambda c 1 plus cosine theta 1. Then, well, obviously those cosine terms will go away. We will left with 2 lambda c. So 2 lambda c can be calculated from your the list of constant, yeah? Slide. So we set the equation for the first scattering and then second scattering, and then when I identify this angle, you can actually combine those two equations, which will give us 2 lambda c, and then our wavelength difference is 0.00485 nanometers, which is very, very small. Yeah? Now let's look at the question number 2. An incident photon with a wavelength lambda is scattered by a rest electron. After the scattering, the wavelength and the scattering angle of the scattered photon are lambda prime and then 90 degrees. So scattering angle is given, and then express the angle of the scattered electron with the refractively incident photon in terms of lambda. So here, now we want to find this scattered angle for the electron. So we cannot simply use the quantum effect because in the quantum effect equation, we don't actually take into account the electron. Alright? So quantum effect equation only have the incident photon and the scattered photon. So in order to find this scattered angle for the electron, we are going to use this conventional the physics, yeah, such as the conservation of momentum or conservation of energy. So I'm going to draw this diagram, okay, for to illustrate this event. So we have an electron, okay, at rest, and then incident photon, okay, with wavelength lambda is scattered to 90 degrees. So our scattered photon is going to be drawn in this, all right, and then the angle is going to be found here, so it is 90. And then this scattered photon has the wavelength of lambda prime, and then the electron is also scattered somewhere, alright, and then the angle, I would say this is phi, is not given. So we want to find this angle phi. Alright? So if I set this quantum effect equation, this will go as lambda minus lambda prime equals lambda c, 1 minus cosine angle theta. And then obviously this angle theta is 90 degrees. So what is cosine 90 degrees?
0.
Cosine 90 degrees? 0, yeah? So we will have lambda c only. So we can immediately find the relation between lambda and the incident photon and the scattered photon. Okay? But then this does not help us to find this scattered electron angle. So what we are going to do is we will use the conservation of the momentum. So I'm going to introduce coordinate as this. Okay, so this is going to be our x-axis, and then this is going to be our y-axis. Then we have x and y-axis. Then when our momentum must be conserved, so I will set the equation as T of this incident photon. The momentum of the incident photon must be same as momentum of the scattered photon plus momentum of the scattered electron. Yeah? And then this angle is not in along the x and the y axis, so I'm going to use decompose this to the x and the y component. Yeah? So along this x component.
By that
Along this x
constant,
component, we have to keep it. So instead the photon is along the x-axis.
1 over r.
Equals the scattered photon. Okay, the scattered photon has no x component at all. The scattered photon is aligned to the y-axis. So this is going to 0. Alright? And then finally, our electron will have the potential as P times cosine. Alright? Then we can also set the equation along this y-axis as P. So incident photon is along this x-axis, so there is no y component. So incident photon along the y component is going to be 0 equals P prime, which is aligned to this y-axis, plus Pe times sine pi. Okay, for this scattered electron. And then you see that this electron scattered according to my coordinate, okay? According to my coordinate, this electron scattered to the negative direction, so negative y direction. So I will have minus sign. Okay? Then my PP, which is the instant the momentum, is actually h over lambda, isn't it? Equals PE times
Do you know why the
cosine
y
phi.
is 0?
And then from
why
this
is
second
this
equation,
zero? Like,
we can
because
also see that this scattered photon momentum is h over lambda prime is going to be PE sine
所以你的 notes have
Yeah,
phi,
why you draw?
and then lambda
Why you draw like
prime
this?
was related to this lambda as
It's like
this.
video.
So this will be go into this second equation, and but this will become lambda over
那个你 photon
lambda minus lambda c.
photon 会
Okay?
但是
Equals
那个可以拿出来 we go down all the
So
electron
where equation 1 and equation 2, you are going to divide equation 1 by 2, then your PE will go away, then we will have to get the cosine phi and sine phi, which will lead us to the relation between this angle, scattering angle, and then the wavelength. Okay? So we first set this the coordinates, and then according to the conservation of momentum along the x-axis, we have one equation, and then along the y-axis we can set the second equation, and then we just combine those two equations, okay, to find the angle. Now I'm going to jump one of the past questions. So AY 2021.
1006.
Alright, so
你也配
a photon with a wavelength of lambda 0 is instant on an electron that is initially at rest. After the interaction between the photon and the electron, the photon scattered in exactly the opposite direction, okay, relative to this instant direction. Now, from this, we first want to calculate the momentum and the energy of the scattered photon, and also momentum and the kinetic energy of the scattered electron. So, using this quantum effect equation, we can find this momentum and the energy for the scattered photon. Okay, because the lambda prime or the wavelength of the scattered photon can be calculated. Okay, then the momentum and the energy are related to this wavelength, so you can find it. Then, well, in order to determine this momentum and kinetic energy for the scattered electron, where the quantum effect itself is not 100% useful yet, so we have to use this conservation momentum and the conservation energy. Alright? So I will do a diagram, alright, to illustrate this scattering event. So the electron was at rest here, and then our incident photon comes into this direction with a wavelength of lambda 0. And then this photon is set off to the opposite direction, okay, as this with lambda prime. Okay, then what would happen to this electron? Because this instant photon is returned to this original position, so the electron will just push along this same horizontal axis, isn't it? So this is going to be bound to that. So then, when I will set this coordinate again, as this. And then, well, you can easily see that there is no y component at all. So we don't have a y component, we have only x component. Alright? So, let's first apply this quantum effect, which will take lambda 0, lambda prime equals lambda c. 1 minus cosine theta. So in this case, what is our angle? So for this scattering, what should be our angle? 0 or 180?
180.
180, yeah? So this is equal to 180. And then cosine 180 is?
Minus 1.
Cosine 180? Minus 1, yeah? So this becomes then 2 lambda c. Alright, so then your lambda prime is going to be lambda 0 minus 2 lambda c. Alright, so Now this is going to be used to determine the momentum of this scattered photon. Okay, h over lambda prime, so h over lambda 0 minus 2 lambda c, and then energy of this scattered photon, which is hc over lambda prime, so hc 1 over lambda 0 minus 2 lambda c. So now we determine the momentum and the energy of the scattered photon. Yeah. Now let's move on to find the momentum and the energy for the scattered electron. Okay, scattered electron. So we will use this conservation of momentum and conservation of energy. So my conservation of momentum will be written as P, the photon of each of the photon momentum is going to be the scattered photon momentum plus the scattered electron momentum. Now you can see that this electron goes along the same direction, but the scattered electron is going to the opposite direction, therefore I'm going to put minus. Right? And then for our energy of the photon is going to be the energy of the scattered photon plus the energy of the scattered electron. Therefore, my PE, so PE is going to be PP plus PP prime, which is h over lambda plus h over lambda 0, okay, lambda 0 minus 2 lambda. And then my energy of the electron is going to be EP minus EP prime, which is going to be hc over lambda 0 minus hc over lambda 0 minus 2 lambda c. So now we determine all those momentum and then energies for the scattered photon as well as scattered electron. Yeah? So we first start with this conservation of momentum and energy, and then from the quantum equation we can find the de Broglie wavelength for the scattered photon, which can be used to find this momentum and electron of the scattered photon. Yeah? Then with this we are going to find this momentum and the energy for the scattered electron and this. Right? So then let me go back to this original tutorial questions. Alright, question number 3.
Yeah.
A monochromatic beam of light is
What kind of
observed
reserve?
by a collection of ground state hydrogen atoms in such a way that 6 different wavelengths are observed when the hydrogen relates back to this ground state. Then what is the wavelength of the incident light? So here it states that 6 different wavelengths. So we should be able to see 6 different color lines. Yeah. So this is from this hydrogen atom. So let's try to apply this energy diagram. So when we consider the simple 2 energy levels, then the electron excited to this upper level, when it decays to this lower level, this will generate frequency, okay, or the wavelength. So we will have only one wavelength. So it seems like we need more than 2 energy levels, right? So I add another energy level to this state, energy state is 3. With this, you can see that if I name it the first emission as F1, then we can expect another emission from the 3 to 2 as F2, and then another one from 3 directly to this 1 as F3. Okay, so then we have 3 different emissions with the 3 levels. Now let's expand this for 4 energy levels, 1, 2, 3, 4. Okay, then the excited electron to this energy level of 4 can come down to this next energy level with emission of F1. This can also decay to the subsequent level as F2, and then we are going to have F3. Alright? And then this one can also decay down to this N2 level, which will generate F4. Okay? Also, the electron at this third level can also decay down to the ground level with frequency of 1. And then finally, the electron in the level 4 can directly come down to this first level at F6. So it seems like we need 4 energy levels to enjoy 6 different emission wavelengths. Yeah? So now we see that we must have 4 energy levels. Then, in order to have these emissions, the first requirement is the electron on the first level must be excited to this uppermost level. Okay, so this is the very first condition. So then, what should be the wavelength? Okay, what should be the wavelength to make this excitation? Okay, so this wavelength must be matched to this energy level difference, isn't it? So our energy level difference is going to be E4 minus E1, and then this is matched to the photon energy, so HF. Okay, so now how are we going to define this E4 and E1? They are related to this hydrogen atom, isn't it? Hydrogen atom, therefore we are going to use that equation. Okay, this equation is also available in your list of the formula. So this is going to be minus, what is this? Minus 13, yeah? 16. Is it 16? Okay, let me have 13.6. So this is going to be 13.6 electron volt over 4 square minus 13.6 electron volt plus 1 square. So you can calculate this, which will relate to this HF, which is H times C over lambda, so we can define this number. Right? So,
first
of all, we know that we should have the 4 energy levels to enjoy the 6 emission wavelengths, and then the first requirement is that the electron must jump from E1 to E4. Therefore, this energy difference is now related to this energy difference is now related to your photon energy, yeah? And that's the wavelength. So our wavelength is found as 97.5 nanometers, right? So let's move on to the next question. So wave function for particle is given as it is. So this equation is a bit broken.
这个是那个Jungle 7啊，
I have time.
因为我不知道这个东西，Jungle 7，
Okay.
我没有看。
And then we want to find the probability, okay, that the particle is located between -8 to +8. So when we are given this wave function, then most likely we are going to calculate the integration, isn't it? So this is the mathematical
1 over
calculation.
x square plus a square, whole thing square.
Our wave function is given as
在哪一个 tangent 哦？我不有去 Google 的
a
final
over pi x squared plus 8.
很难用的。
Alright, and then our probability from -8 to 8 is
Okay, you do.
calculated as this.
老师觉得，
So
等一下没有做一下，
一天做的。
我去，这个回去看。
okay, so this is our probability from -8 to
Google,
8.
this Google.
Right, so then this becomes
Hai lo tu per troppo.
a over pi x squared a squared dx. So a over a and pi, they are constant, so I will take out them from the figure, so this becomes pi 1 over x squared plus a squared dx. Okay, then we need to do this integration, and then I know that over x times 1 over a.
他的
Okay, so
1 over
v minus a. Right?
One
So
over-
then
Oh, there's a formula for the
a
Yeah,
will go away. So I left with 1 over pi.
Yes.
And
1 over
tangent
something
of
is not.
a over a equals to tangent of
There's a
one
for this.
minus
And then
tangent of a over minus a equals to minus 1.
Wow, it's Google.
Alright? So what is the tangent to after tangent to 1? Your after tangent to 1 is 4 over
Sorry.
pi. Isn't it? Oh, sorry. Pi over 4. Yeah? And then minus tangent is a tangent or after tangent minus 1 over after tangent is going to be minus 3 over
Electron 也是有一点这样的，
sorry
你记得EMV electron element
Okay, so
electromagnetism
pi will all go away and then we will left with
它
1.
的 first part 有一
So
点
probability of finding this upper is going to be 50%. Okay? So this is our probability, and then you can calculate this integration, and then we find this probability is 50%. Okay, and then you may want to find this integration is difficult, and then my suggestion, okay, is that you may want to memorize this integration. Alright, so we actually
很快啊。
have a few difficult integrations, okay, throughout this course. So in the electricity magnetism as well as in the quantum physics, and then you can see we use very similar type of this integration. So my suggestion, because of that reason, my suggestion, you just memorize this to this, okay, rather than go through very long calculation. Alright. So then I'm going to move on to the next question. So question number 5. A photon with wavelength lambda is observed by an electron confined to a box. As a result, the electron moves from 1 to 4. Find this length of the box as function of lambda, and then what is the wavelength of the photon emitted in the transition of that electron from 4 to 2. So now here we consider a particle, okay, in a box with length of L, and then the particle was initially in the state over 1, and then it jumped to state over 4. Okay. And then we want to find the relation between the box length and then the wavelength of the particle. So I know that some of you are tempted to use this. So, well, this length and then this wavelength is already related as wavelength equals 2L over N. So we already know this. So, well, this is the answer. Okay? But please don't do so because here the energy transition is already given in the question. Okay, energy transition is already given in the question. In other words, we must use this energy, or we must find the relation, okay, accounting for this energy transition. Alright, so in other words, we are going to find this energy associated to this energy transition, and then this energy is going to be converted to this wavelength. Okay, so if you attempt to use this equation, please read the question more carefully. Okay, if you are given the energy transition, then you are going to use this energy transition, and then it's a relation to it's associated with wavelength. All right. So when we are given this particle in a box, then your energy, okay, of this particle at the end state is given in the list of the formula, and then this is given as h squared n squared over 8m Okay, so this is where we have this energy level. Okay, now the electron or the particle jumps from n equals to 1 to n equals to 4. So its corresponding energy difference is going to be found as E4 minus E1, isn't it? So this becomes h squared over 8ml squared 4 squared minus 1. So then this becomes 15 over 8 h squared 8ml. Okay, and then this is related to your the photon energy. So this is alright? So we assume that the particle jumped from the first level to the fourth level by absorbing the photon energy. Okay, so now this is C over lambda. Therefore, our wavelength is going to be
You need to do substitution.
hc times, okay, we don't have so hc times 8ml squared over 15 h squared. We don't have this is s squared, so this is s squared. So then where h and then where we go away, so we will have 8mc over 15h. So we find this wavelength in terms of and s squared, wavelength in terms of the box. Okay? Sorry. The question is to find this expression for the box. So we have to write this again for this L. So this L here is going to be then L squared is going to be then 15h times lambda divided by 8mc. Therefore, our length is going to be 15h lambda over 8mc, and then we have the square root. Yeah. Now, this particle at the fourth level, now drop to the second level. Okay, and then we want to find its wavelength. We want to find its corresponding wavelength. So again, we are going to repeat this calculation for this energy transition. So we will set the equation as delta E equals E4 minus E1, which is going to be h squared 8ml squared 4 squared. This is 2, yeah, minus 2 squared. So this is going to be 16 minus 4, so square h squared 8ml squared. Alright, so I may happy with this, but then I already know that this length is already found in terms of this wavelength. So I want to substitute this into this equation. Okay, then let me do that. And this is going to be 12 h squared 8m times 1 over s squared. So this is going to be 8mc over 15h and then lambda. Okay, so this now reduced to 4 over 5 h over 8 h over lambda. Okay, so this is our new photon emitted from this energy transition. So we will have hf lambda hc over lambda prime. Okay, so because we want to find this lambda prime, so h will go away. Therefore, we will have I forgot this C must be here, so C will also go away, so I will have lambda prime is going to be 4. Okay, so our new emission wavelength is longer than the initial wavelength, which makes sense because this corresponds to the energy transition from 4 to 2, yeah, and then this is transition from 4 to 1. So as you can see here, this energy transition will have higher energy. Okay,
对啊，
therefore
哦呀，对
its
对对，
wavelength
我
is
在想为什么
shorter.
那个 square root 不见掉，没有看到。
不会做啊，不然问题。
So we will find this box and box length and the wavelength relation, okay, associated to this energy transition, and then we can also find this new wavelength generated from the physical energy transition, and then well we can stop here, but then we already know that this box length is box length is
哎，弟，不要再剪包了。
related to this original wavelength, so we just will
哦，
substitute
我没有剪上面
this
的。
你要跟他讲，你不要剪。
and then
我没
we
有是
have
剪旁边
this
后面。
如果你没有
final
讲的话，你剪
answer. Okay,
这
so
个 scissors be like
啊对，
emission
他
wavelength
每次
is
剪，我
longer
不
than
该讲不要剪薄，他有一
the
样。
wavelength.
懂，但是我没有剪上面。
So I have a couple more positive questions.
但是我剪来很短的。
So positive question AY 1920.
很薄。
A collection of electrons are accelerated from left by a potential difference. Potential
本来
difference.
每两次会剪包，不能。
So electrons
不要很顶的。
are at rest initially. Okay, so electrons were happy, okay, at their original initial condition.
可是我不要。
Then the potential is applied to this electron. Then what will happen? Because of this potential, this electron will now travel, yeah, will now travel, and then accelerated, which means the potential energy is now converted to the kinetic energy, yeah, now converted to kinetic energy. So the accelerated electrons are then perpendicularly incident onto a clean nickel crystal surface whose crystal lattice constant is largely. So when these dots illustrate the atoms of the nickel, yeah? And then most of the electrons are diffracted by the atom on the surface in the direction of angle phi with respect to the incident electron beam. So the electrons are diffracted, okay? So here, the question already defined that this is diffraction rather than scattering. Okay, so we have this diffraction, okay? With this observation, we want to determine the wavelength, and then the diffraction angle, and then for the first diffraction, and then also second diffraction. Okay, so first of all, the electron beam. Okay, so electrons are so small, therefore, while we can use this de Broglie wavelength, yeah, so the duality of the wavelength particle. So now we are going to treat this electron beam as a wave. Wave means it should carry some wavelength. Okay, and then this wavelength, when it incident on this nickel atom, it is diffracted. So now we have the diffraction tool. Okay, so you can see that this atoms, the lattice constant is repeatedly appears along this atom, which means this crystal lattice now serve as the grating, okay, for this electron. Alright, so we can set this equation. This side, that,
I think we do have 50 and 1.
okay, and then
No,
of course your m is the diffraction, okay, order of the diffraction, and then this wavelength of the electron beam. Okay, so we are going to determine this electron beam under the first condition, right? So
But
so again, this is okay. D sine theta is going to be plus minus m lambda, and then I'm going to drop this negative sign because well, it's not our interest, yeah. So I'm going to just drop it. Okay, m lambda. Now let's first try to find this lambda, which is the wavelength. So potential is given as 54. Alright, and then this potential is going to build up this potential energy, and then our potential energy is going to be potential times its charge, therefore we consider electron, therefore this is going to be 54 electron volts. Then this potential energy is converted to this kinetic energy, isn't it? And then, so when the electron is about to hit this atom, it will have the maximum kinetic energy. Yeah? So we can consider that this all the potential energy is now converted to the kinetic energy. So our kinetic energy is actually potential energy, and then our kinetic energy, potential energy, which is 54 electron volts, and then we know that this kinetic energy is related to this momentum because we want to use this Dubrovy wavelength. Yeah? This is connected to this momentum as p squared to m, okay, from the classical physics. Then what is p? P is h over lambda, isn't it? H over lambda, so it's going to be h squared lambda squared times 2. Of course, this is the mass of the electron, okay? Then we will just solve this, okay? For the wavelength, the h and m are constant, so we can solve this for the wavelength. So we determine this wavelength. Right. Then we will use this equation now. So t times sine this phi is 50 degrees. Okay, under this 54 volt of potential, this diffraction angle is given at 50 degrees. So this is going to be 1 times lambda for the first order diffraction. Okay, so wavelength was just determined, therefore you can just solve this for the atomic lattice constant. Okay, so the lattice constant is now determined. Right? Now we move on to the second question. Now this potential is changed to the 50 volts, and with that we want to find this the diffraction angle when m equals 1 at the first order diffraction. So again, we are going to use this equation again. Okay, but then this potential energy or the total energy now change to 50 electron volts. Okay, so we are going to solve this for this wavelength. When the wavelength is determined, we are going to use this equation. Yeah? 1 times wavelength. Wavelength is just calculated, and then this the lattice constant was determined from the previous question, so you can solve this for this equation. And then the third question is whether we can see the second order diffraction. So now order of diffraction is increased to 2. Then we are going to repeat this calculation. So d sine phi equals 2 times lambda. Then because we want to find this angle, so sine theta is going to be 2 lambda over d. Alright, and then those numerical values are already determined in the earlier fraction. So you if you just substitute those numerical values, you will see that this is larger than 1. So of course this does not make sense, therefore we are not going to see the second order diffraction. Okay? We will only see the first order diffraction. So this is our actual working. So we now treat this nickel crystal as a grating for the electron beam, and then because this potential energy is given, this is going to convert it to this the kinetic energy, and then we will set the equation which will be solved for this wavelength and this, right? And then this wavelength is going to be used to determine this lattice constant, and then we change this potential, and then this the different potential will induce a different diffraction the wavelength. Therefore, we can find this diffraction angle for that wavelength. And then when we move on to this second order diffraction, then where we found that sine phi is actually larger than 1. Therefore, we don't see the second order diffraction.
My question is p
right?
I mean moment.
Now let's move on to the
보냈던 것도
next
less than
fraction.
that.
So this is a positive fraction, ay factor 21.
There wasn't really in the square.
And then we are given
square
the wave function, okay, and then
Oh.
we want to find this
square
express d in terms
This
of
m
the
square b
vector,
square.
and
Okay,
also
so
want to
consider
find
m.
the
Yeah, sorry.
probability. And then the probability is given as it is
This is p
within
square.
this range, and then we
p
want
square
to
equals m
find
square
the
b square.
expression for
这个上面是 divide 2 m
and
so
then
m 等于
find this
上面会有一个 m
probability from
那 b
minus
square 已经
delta
记了
to the infinity.
所以
So right here, wave function is given again. So most likely this is going to be the mathematical calculation. Okay, mathematical calculation. So let's try to solve this. And then first of all, we want to find this the express, okay, d in terms of vector under normalization condition. So what does this mean? So after normalization, this probability becomes 1, isn't it? With the normalization, the probability becomes 1. So we are going to use this normalization condition. Alright, so our wave function is given as d exponential minus beta x when x is larger than 1,
I know.
or d exponential beta x when x is smaller than 1.
xx.
Right? And then after normalization, we know that the probability is for minus infinity to
National
the
BJJ.
infinity square dx must be 1. Okay, so we are going to use this to
BJJ.
find the relation between large d and then this vector. Right? So let's calculate this. So this becomes so well here our wave function is actually in two different forms, yeah? Depending on the region. So I'm going to expand this to the negative region and the positive region. Okay? Because we are given different wave functions. So in the negative region,
这和那个 physics 的 assignment 啊是 Check this
d
out.
square exponential 2 beta x dx. Right? And then for this positive region, this becomes 0 to the infinity. Okay,
Oh,
d
it's all right.
square
It's all
exponential
right.
minus 2 beta x dx.
泰国
Right? So
先给
let's do this integration. Then this becomes d square over 2 beta and then exponential 2 beta x, okay, minus infinity to the 0. And then for this positive region, we are going to have d square over minus 2 beta exponential minus 2 beta x dx. Okay, so then this becomes 2 beta. Exponential 0. Exponential 0 is 1, yeah? Exponential 0 is 1, so 1 minus exponential minus 2. So and then exponential minus infinity is 0, yeah? Very good. So this is 0. Okay? Plus d square minus 2 beta exponential is 0 to the infinity. So exponential minus infinity again 0. And the exponential minus 0 is 1. Yeah? Then this becomes, so we have 1 and then minus minus again 1. So this becomes d square over 2 beta times 2. And then, because this is a normalization condition, so this becomes 1. Therefore, our d is going to be square root. Now, one thing you may want to pay attention is this. So, from our calculation, we now discover that the integration in the negative region and the integration in the positive region. So this is our integration for the negative region, and this is integration for the positive region. They actually the same. They actually the same, isn't it? Therefore, this negative region integration is 1 over 2, and the positive region exponential, yeah? So 50%.
when doing signals
Alright? So this is our conclusion. What another conclusion? Okay. Now, let's move on to this next condition. Now we want to find another expression when the probability from minus delta to delta, okay, is 1 over 2. Okay, then what's
저
the
signals do
relation
what
between
do
delta and delta?
those
So
signals.
we want to find it. Okay, so let's do this calculation one more time. So again, we need to split this into the negative region and the positive region, yeah, because we are given different wave functions. So for this negative region, this probability is going to be from minus delta to the plus delta. V square exponential 2 beta x dx plus for the positive value, this is a positive region, this becomes v square exponential minus 2 beta x dx. Okay, so we will do the integration again, and this becomes v square 2 beta exponential 2 beta x minus delta to 0 plus v square minus 2 beta exponential minus 2 beta x from 0 to delta. Alright, so then this becomes v square 2 beta exponential 0 is again going to be 1, yeah? And then we will have minus exponential 2 beta delta. Okay? And then plus we will have v square minus 2 beta exponential delta. So we will have exponential minus 2 beta delta. And then exponential 0 is 1. So minus. Okay? So then let's combine this. So we have minus sign, so this converted to plus 1. Yeah? So we have 2, so v square to
因为
beta
这个
2.
会上你的，
And then minus
这个
minus,
上
so
面
we
的
have
这个
minus
整个会变成 infinity，
2
这个
minus
上面变成
exponential, so this is
for integration 的
exponential minus 2 beta delta. So
negative
in other words,
infinity
2 v square, so 2 will go away, so v square over beta, 1 minus exponential minus 2 beta delta. Alright, and then this large d is actually square root of beta.
sub infinity.
Okay, so this large d
The
is
x
square
is
root
up
of beta, so this now becomes
negative infinity.
so this will go away. So we will left with 1 minus exponential minus 2 beta delta is 1 over 2. Okay, so this probability is given in the question. Alright, then which means this exponential minus 2 beta delta must be 1 over 2. Isn't it? Therefore, I'm going to take this ln function, so logarithm, then ln 2 beta delta, okay, going to be ln 1 over 2, so minus ln 2. So, okay, sorry. So I'm going to take the logarithm again, so this is going to be minus ln 2 beta delta, and sorry, so minus 2 beta delta, so equals minus ln 2, therefore my delta is going to be ln 2 over 2 beta. So now we have the expression for the delta and in terms of the beta. Now, another thing you want to pay attention in this calculation is this. So when we split this integration into negative region and the positive region, alright, then you will see that their integration is actually the same. Their integration is actually the same. Yeah, actually the same. They are actually the same. Yeah, and then when you add these two, this becomes 1 over 2. Okay, therefore each integration is going to be 1 over 4. Okay, because their calculation is the same. Okay, so 1 over 4. Now, let's move on to this, the last question. So now we want to find this probability, okay, from minus delta to plus infinity. Okay. Alright. So again, we are going to split this into negative region and the positive region. So this becomes minus delta to 0. Okay, and then the square exponential 2 beta x dx plus in the positive region is integration from 0 to the infinity the square exponential minus beta x dx. Now, from our earlier calculation, we already know this integration, okay, okay, and we found here this integration is actually 1 over 4. So and then, in the very first question, we already know that this is just 1 over 2. Okay, so this 1 over 2. So when we add both integration, then this is going to be 3 over 4. 3 quarters. Okay, so we have the probability. So I will show you the working. So we first use this normalization condition, yeah? And with normalization, this becomes 1, and then we just do the calculation, and then finally we have this. And then we move on to this second question. So we want to find the probability from minus to delta to plus delta. And then you do this integration, then we find that alright, and then because this square is actually beta from our previous calculation, so this is now reduced to this, and then this becomes so we have the expression for delta in terms of delta. And finally, we want to calculate the okay, so we want to calculate this, yeah, this probability, and then from our previous calculation, we know that this is 1/4, and then this is 1/2. So our final probability is going to be
2 fraction in the end 有4个 term.
So that's it for today, and then please submit your homework by this week.
你是叫我做integration